You're falling. Not like tripping down the stairs, not like jumping out of a plane. No, this is different. You feel it before you see it, a stretching, a pulling sensation that starts at your feet and slowly, relentlessly works its way up your body. It's not painful yet, just unsettling. Like gravity itself is trying to resculpt you, to elongate you into something impossibly thin. You glance down. Your legs look longer, thinner. Your arms, too. It's like looking into a funhouse mirror, but the distortion is real, and it's accelerating. Above you, the stars, once pinpricks of light, now look like streaks, then smears, painting the sky in dizzying arcs. Below, the inky blackness looms, a cosmic maw, swallowing everything, including the very light around it. What's happening? Why aren't you just instantly crushed, as every sci-fi movie ever has promised? The truth is far stranger than simple destruction. You're not just falling into a black hole. You're being stretched into a cosmic piece of spaghetti in a process scientists have quite accurately dubbed spaghettification. But why does this happen? And what's beyond that terrifying stretch? More importantly, if you could somehow survive it, what would you even see inside? That's essentially what's happening to you near a black hole. Its gravity isn't uniform. It's incredibly intense, and it gets stronger, exponentially, the closer you get to its center. So the gravitational pull on your feet, which are slightly closer to the black hole's core, is significantly stronger than the pull on your head. This difference in pull, this gradient, isn't just a gentle tug. It's a colossal, differential force that's quite literally tearing you apart, molecule by molecule. Now, this spaghettification process doesn't happen the same way for every black hole. There are two main types to consider for your unfortunate journey. First, the stellar mass black hole. These are relatively small, maybe a few times the mass of our sun, compressed into a space smaller than a city. For these guys, the tidal forces, the spaghettification kicks in before you even reach the event horizon. That's the point of no return, the cosmic boundary where escape velocity exceeds the speed of light. You'd be ripped to shreds long before you officially cross that line. Brutal. But then you have the supermassive black holes. These are beasts, millions or even billions of times the mass of our sun, dwelling at the centers of galaxies, like our own Milky Way. For a supermassive black hole, the event horizon is much, much wider. It's so big, in fact, that the gravitational gradient across your body, as you cross, it is far less dramatic. You wouldn't even notice. You'd just pass through. Think about it like this. If you're falling towards a tiny pebble, the gravity is super concentrated right at that pebble. Any part of you closer to it feels a massive difference. But if you're falling towards something the size of an entire planet, the gravitational pull, while still strong, is more spread out. So you, the intrepid explorer, would pass through the event horizon of a supermassive black hole without feeling a thing. No flash, no bang, no signpost saying, "Welcome to the point of no return." One moment you're seeing stars, the next, you're not. But if you don't feel anything as you cross, then what does happen? This is where things get truly wild, because your experience of falling into a black hole depends on your perspective. Let's say your best friend, Bob, is watching you from a safe distance in a spaceship. To Bob, you never actually cross the event horizon. As you get closer, your image would appear to slow down, like a terrible internet connection buffering a video. You become redder and redder, a phenomenon called redshift, as the black hole's immense gravity stretches, the light waves coming from you. Eventually, you'd appear to freeze, a ghostly, impossibly stretched crimson, silhouette forever suspended at the edge, never quite making it inside. Bob would never see you truly vanish. But that's Bob's reality. For you, the person inside the spaghettifying noodle, reality is a lot more immediate. You'd cross that event horizon, perhaps completely unaware of it, if it's a supermassive black hole. And once you're inside, there's no going back. Not even light can escape. Every path, every direction you could possibly travel leads towards one single, inevitable point, the singularity. The singularity isn't a place you can just visit. It's not a tiny star or a planet. It's a point of infinite density where all the mass of the black hole is compressed into zero volume. Our current understanding of physics, all the elegant equations from Einstein to Newton, simply break down at this point. It's where space and time, as we understand them, cease to exist in any meaningful way. It's the ultimate cosmic endpoint, and every particle of your now atomized self is hurtling towards it. Now, if that wasn't mind-bending enough, there's the information paradox. This is one of the biggest mysteries in modern physics. What happens to all the information that made you, your memories, your unique quantum state, every atom's precise location and momentum? Does it just vanish forever? If so, it would violate one of the fundamental tenets of quantum mechanics, that information can never truly be destroyed, only transformed. Stephen Hawking famously debated this, suggesting that black holes aren't perfectly black. They actually emit a faint thermal radiation, Hawking radiation, causing them to slowly evaporate over incredibly vast timescales. So, if black holes eventually evaporate, does the information somehow get encoded in this radiation? Or is it truly lost? Some theories suggest the information is encoded on the event horizon itself, like a cosmic hologram. But even that is fiercely debated. It's a puzzle that continues to stump the greatest minds. So why do we even care about such a horrifying, distant scenario? Because black holes are not just theoretical boogeymen. They are fundamental building blocks of our universe. Supermassive black holes anchor entire galaxies, influencing star formation and cosmic evolution. The collision of two black holes creates ripples in space-time so powerful we can detect them, here on Earth, billions of light years away, through observatories like LIGO. They are the ultimate cosmic laboratories, pushing the boundaries of what we understand about gravity, time, and the very fabric of reality. We may never personally experience spaghettification or cross an event horizon, but by imagining these extreme journeys, by pushing our understanding to the very limits of the known universe, we gain profound insights into the nature of existence itself. Black holes aren't just cosmic vacuum cleaners. They are cosmic paradoxes, forcing us to ask questions about information, destiny, and what truly lies beyond, the edge of forever. And in the end, isn't that what science is all about? Staring into the abyss and demanding answers, no matter how unsettling they might be.